We are San Francisco too, and we are Pob, Jimmy, Shide, Pablo, and me, Sara. And our project is called Rooftop Wonderland, also looking at the Mare Island site in California. Next. So I will go quickly through these because the first group did such a good job of presenting the site. But as we know, the Mare Island site is about 38 kilometers from downtown San Francisco, which is accessible by ferry and car to connect the two cities. Next. The site itself is located on Mare Island, which is just across one bridge from downtown Vallejo, and abuts the San Pablo Bay, as we learned in the first presentation as well. Next. And our site itself is located right in the middle of the island, just southwest of the newly planned ferry terminal, and adjacent to low-rise residential buildings on one side, and then industrial buildings to the northeast, I should say. The first thing we did was look to sea level rise, just to understand how that would affect the site itself. And what we see when we look to the NOAA intermediate projections for sea level rise to the site, while Mare Island itself does see quite a bit of change, a lot of the island goes away. We also see that our site itself is not very strongly affected by sea level rise. So we started off by defining some goals, and those goals fell into three main categories: resilience, costs, and health. And within resilience, we wanted to adapt to extreme events. Within costs, we wanted to balance financial costs and benefits. And health, we aimed to create a healthy neighborhood. And within each of those goals, there were kind of main objectives that we wanted to achieve. So we wanted to address sea level rise, which we saw in the site selection is pretty well taken care of, at least in the intermediate projections. Thermal comfort, food supply, and energy supply. And within cost, we wanted to run some cost benefit analysis. And within health, we wanted to develop an urban analog to the 9 foundations of a healthy building, which is a framework that is developed by the Harvard School of Public Health for a building scale. So we were interested in applying that to the urban. And we had at our disposal 7 different tools that we could use to better understand how we are furthering our goals through our proposal. And we added an 8th tool, the health framework, to assess health on our site. So we can see how these tools relate to the goals that we've established. So resilience relates to carbon emissions, energy, daylight, and agriculture. Cost relates to energy cost and agriculture too. And then the health goal relates to many of these different tools that we've established. Next. So now Pablo will discuss the urban strategies that we've established.
Yeah, so with the urban strategy, as mentioned, the site is located in the kind of central part of the Mare Island, and the site is in distance of like 500 to 600 meters away from the industrial waterfront and the ferry terminal. Next slides, please. So with our initial layout of the grids, we try to keep the main street access intact. So we initially came up with this a very generic site boundary measuring 80 times 60 meters. And also currently the site is located in adjacent to a lot of existing parks and open green spaces. Also having this academy university building in the central part of this site. And the surrounding area of the site is also mostly residential, like a very low-rise residential area. So in the initial phase of our project, we kind of explore each of us different kind of proto block designs, giving them kind of a different FAR level, and also looking at like daylighting and the form that this kind of building proto block creates. And then we eventually pick the design number 6 to develop further, as it has it kind of satisfied a nice amount of daylighting at that time, which is about 37 SDA, and as well as we kind of see this potential in the central courtyard and the stepping roof typology. So we then kind of move on to kind of rearranging this in this side, the given side area. We kind of just like directly put this in the proto blocks, but then we can see that because the initial proto block kind of occupy this 80 times 60 side area, and then they're kind of separated by the street, which is 8-meter street, and then there are no kind of like pedestrian walkway, and also we see that this it's getting pretty flat and generic. So as we develop further, we kind of adjust this. We shrink the site down, given 6-meter pedestrian pathway, as well as looking at like the FAR, like placing strategically FAR, because I think we kind of all agree that we don't want to build a separate like high dense with like a high rise or like a tall building in the site. So we kind of go with this, having like a higher building in the central part, and then we kind of lowering and stepping the surrounding blocks from the center part out to the surrounding to create like this more kind of nuanced transition to the surrounding residential area, as well as creating like the whole urban as like this kind of continuous landscape in a way, and also maximizing the views to the waterfront. So with these reorganizations of the proto blocks, we have come up with the two kind of generic proto blocks, which the first one being this kind of developed courtyard typology. We kind of also play with at different levels of the rooftops, and also with these options, they're also varied in the height. We also puncture the ground to create better accessibility, as well as promoting ventilation. Next slide, please. This is the second type of the same topology, which is lower. This type of proto block is located in the front part of the site, which is close to the park, as well as have like a full frontal waterfront view. And the lowest, the smallest proto block in here, it's located on the surrounding perimeters of the site. All of them kind of have more than 40 SDA, and also the last typology of the proto box, which in the urban scale, they created a bigger this pocket courtyard that would also serve as a more public spaces area for like a weekend's market or any kind of future build, given that our site is one of the sites that is not affected by the resilience or the sea level rise problems. We see that we also would like to provide like more spaces in our site for future development in a way. And just go quickly the main street. As we keep this kind of main axis connections to the existing street, we also having like this clear axis of the main street that we see that all the amenities or the commercial and retail programs will be placed along this axis. Next slide, please. Yeah, an overview of how the programs are distributed. We actually aim for like a more mixed use, but as the overall overview of like the dominant programs will be the kind of north and western part will be more a residential area, which connect to the existing residential area. And yeah, we have around 210,000 square meters of residential. And then we place more the commercial and retail. The retail will be scattered along this kind of corridor, like this clear main street that we have mentioned earlier. And then we kind of place most of the commercial also in this kind of frontal part, which is have like this close connection to the park, as well as the waterfront view. Yep. And also with our kind of generic courtyard typology, we created this kind of an interconnected networks of green corridor as an underlying layers. And well, this also reflects the existing park and open spaces as well as it's the connections of the green space that connects to the park, as well as we also imagine next slide, please. Yeah, how this corridor could extend out in the future development of the waterfront area, which will probably mean more like public revitalization of this waterfront arena. Yeah.
As the name of our project indicates, and also in order to meet our 3 goals, we come up with some rooftop strategies, including rooftop farming, PV roofs, and green roofs. So in order to know what would be the best locations to implement each of those strategies, we did a radiation analysis to find out which rooftop best suits our purposes in terms of having green roofs or rooftop greenhouses or PV roofs. So, for example, here you can see these buildings are the buildings that have the potentials to put the PV panels on top of them. And why we chose these 4 buildings, I'm going to get back to this one later on in our presentation. And here you can see the distribution of the rooftop farming. So we investigated the rooftop farming potential in our site, and by doing so, we somehow wanted to address our 3 goals. And as you can see here, some of these goals, such as the resilience and health, are compatible with each other. On the other hand, the resilience and cost, they are in some kind of trade-off with each other. So, for example, if we want to maximize the crop yield, there's going to be a decrease in the profit that we can get. So by putting and gathering the information from our site and trying to finding a balance between those 3 goals, we reached the conclusion that almost 1/3 of the required food can be locally produced. That would not only result in creating 43 jobs, but also it could provide us with some monetary profit, as well as some savings in terms of carbon emission. And also at the intersection of our 3 goals, it's the operational energy analysis. And we did this analysis by comparing 2 models, the baseline model and the more advanced protoblock. And for the baseline model, we use the base code compliance model. For the advanced protoblock, we use double installation, and we use more efficient lighting and window systems. And by doing that, you can see here that there is going to be almost 22% decrease in the operational energy use. We also did embodied carbon emission, and in the time span of 16 years, as you can see here, using the proposed advanced protoblock would result in 12% reduction in greenhouse gas emissions. And most of this reduction is related to the operational emissions. So even though at the beginning we start with a slightly higher carbon emissions by using the advanced protoblock, when the time passes, the operational efficiency of the advanced protoblock would make such a difference of 12% in the greenhouse gases emissions. And you can see here that the carbon payback period is 7.5 years worth of operational energy emissions. More on the resilience side, though, we have the issue of district energy systems and supply energy. And you know that our site is an isolated chunk of land, and we wanted to answer this question. So what's going to happen if there is going to be an extreme event such as natural disaster or any kind of heat waves? So we wanted to know if those events happens, and due to that, there is going to be a cut in electricity grid from the main island. Would there be enough on-site energy supply to meet the demand of the island? So we considered 2 scenarios, baseline and all electric, and we wanted to provide the local energy supply by adding the PV panels. So in the baseline case, we don't have any PV panels, but in the all electric, we added the PV panels, and there is no gas involved in the all electric scenario. And by doing that, you see there is going to be a huge reduction in the carbon emissions by 80%. And on the other hand, we have 18% increase in the cost by switching from the baseline scenario to all electric. And from the residents' point of view, if we want to have 0.6 ton of CO2 per occupant reduction in carbon emissions, each person should spend $120 more when we are moving from the business as usual scenario to all electric scenario. And out of this district energy system analysis, we found that the area that we need to put our PV panels, it's going to be almost 3% of the total area of the rooftop that is available. So by using that number and the output of the radiation analysis, we came up with these 4 buildings to put our PV cells on top of them to meet all their requirements. Moving towards the cost aspect of our project, we did a cost-benefit analysis with a focus on PV panels. So by considering the installation, operation, and carbon cost on one hand, and also incorporating the benefits that are coming by using the PV panels on the other hand, we found that the net present value of this scenario would be almost $140 per square meter, with the payback period of 13 years, considering the lifespan of 25 years lifespan of the PV panels, and also this investment would result in internal rate of return of 6%.
So we did say that health is a major goal of ours, and we haven't really addressed that aspect very much in our analyses thus far. So we've also wanted to think about walkability and amenities. So if you remember, we had established these kind of 4 main axes across our site, 2 running perpendicular to the waterfront, connecting the residential to the waterfront itself, and then 2 axes paralleling the waterfront. And what we did was we started to map different amenities across the site and arrived or across these main axes to activate them on a pedestrian level, and arrived at a walk score of 81. And that being said, this walk score does not then take into account next the fact that we've got ample green space across our site connecting these different amenities. And I think what's important to think about for these different axes is what the experience is actually like from the perspective of the pedestrian and bike users. So we use this tool called Street Mix to kind of get a sense of what the street could actually be like to use. And so for these main axes, we imagine kind of a one-way kind of scenario for cars and buses, if there are buses on Mare Island. And then go back, please. And then please, dedicated bike lane for bikes, and then ample sidewalk space. And then moving to the smaller side streets, we could imagine kind of single lane traffic for cars, dedicated bike lanes, and very ample space on the sidewalks for pedestrians and cafes, etc. And then we do imagine that some streets might not have any cars, and they would simply be bike zones. And I think this is a good opportunity for us to promote human-powered mobility and reduce the car traffic on the island, which is already kind of limited by the fact that there's a single bridge connecting Vallejo to Mare Island. The next thing we wanted to think about, both in respect to health and resilience, was outdoor thermal comfort, again using UTCI as the index. And we did a much more simplified analysis relative to the first group's work, where we were just simply looking at what is the thermal comfort heat map for an unprotected and unshaded scenario, which you see here, green indicating no thermal stress, which you see during the middle parts of the day, mostly throughout the year, and then light blue and dark blue indicating slight and moderate cold stress, respectively. And I think the reason we were really driven to do this analysis was we're calling this a rooftop wonderland. And so if those rooftops aren't comfortable places to be and occupy, then we don't really have a successful project. So we looked at this unprotected, unshaded scenario, and then we moved forward with looking at a protected and shaded scenario. And you see here that given San Francisco, and this is the San Francisco airport data, so it's not Mare Island specifically, but you see no thermal stress in this scenario, which gives us some insight as to how those rooftops might be designed with canopies and places for people to sit and occupy that are sheltered from the wind and sun. And then lastly, to kind of wrap up all of our health goals into one metric, we developed a healthy neighborhood score that looked across these 5 categories. So we looked at air quality, noise, active design, nutrition, and biophilia. And within each of those categories, we looked into a few different subcategories and tried to assess how our neighborhood would perform with respect to these metrics. And as you can see in the yellow, our neighborhood does pretty well with the scorecard that we developed. So we arrive at an overall health score of 91. I think this is kind of a work in progress because we've developed it for this project. But it'd be interesting to understand how it works in future other projects. So in summary, we've had these 3 goals. They relate to the tools that we've used, and with carbon emissions, we were able to see 79% reduction through an all-electric district energy system. With energy, we saw a 22% reduction using our advanced protoblock, which looked to insulation, advanced lighting, and advanced windows. With daylight, we had a 45 to 50% SDA in our protoblocks. We saw a walk score of 81, 13-year payback for the PV, and 27% of our food grown on site. And then we saw in this new health score that we have a health score of 91, so we have a pretty healthy neighborhood. So that's what we've compiled for you today, and we thank you.